All right, greetings YouTube, beautiful mind here. I hope everyone is doing well. So let's see, we are nearly to the end of chapter 2 on our discussion on exponential and logarithmic functions. This presentation is over section 2.5 applications, exponential decay. A few objectives that we like to discuss. We like to find a function that satisfies dp by dt equals negative kp. We like to convert between decay rate and half-life, and we like to solve applied problems involving exponential decay. The equation dp by dt equals negative kp, where k is positive, shows p to be decreasing as a function of time, and the solution, p of t equals p naught e to the negative kt, shows to be decreasing exponentially. This is exponential decay. The amount present initially at time t equals 0 is p naught. So I think in the previous section, we solved an application with a similar equation, but we were considering like doubling time, right? So this is a kind of a repeat of what we did before, but instead of exponential growth, now we're considering exponential decay, right? And the main difference is this negative causing exponential decay, right? Okay. That's what we did before. So here's an example of like what we were working on before with exponential growth, where k is positive. I notice there's no negative there. So then with exponential decay, it takes on this form. Notice you still have your horizontal asymptote. And it's the same, it's just that now you have a negative in your exponent, and again, your k is still positive. Okay. 10, last time, again, we discussed doubling rate. So now we can consider the analogous of that would be, instead of doubling rate, you can talk about half-life, right? So the decay rate k and the half-life t are related by kt equals natural log of 2, which is approximately this, right? Or the decay rate, you can express it as a natural log of 2 over t, right? And we kind of talked about where they came from before. If you start with like the exponential growth model, you'll get the same thing. It's just that one is talking about doubling time and one is talking about decay rate, all right? And so once you have this, kt equals a natural log of 2, you can isolate, you can rewrite this, like for instance, if you divided both sides by t, right? If you divide both sides by k, you get this one, right? Yeah, I think this one is the easiest for me to remember. Kt equals a natural log of 2, and then you just adjust it based on how you need it. Boom. It says that plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about 0.0028% per year. What's the half-life, right? So I'm just going to do a direct application of what we just introduced, right? So again, I told you the easiest way for me to remember was kt equals the natural log of 2, right? Since we're doing half-life, let's see what else do we have. The k rate. So then now they give us that k equals 0.0028%, right? What's the half-life? So they want us to solve for t. So then if we divide both sides by k, the half-life is going to be equal to the natural log of 2 divided by the rate. Again, this rate has to be expressed as a decimal. So whenever you see that percent symbol, one way I remember is that the percent symbol, you can consider that as 1 per 100, right? So then basically what we're going to get 0.0028, we're going to say times, or percent, you just replace the percent symbol with 1 over 100. Okay. So now we're really just saying 0.0028 times 1 over, or divided by 100, you know, however you want to look at it, right? Okay. So then you just crunch the number. I think I might just use Siri. But then we can see. It's 100 times the natural log of 2 divided by 0.0028.
4,755.3.
nearly 25,000 years, half of plutonium-239 should remain. So if you however amount you start with, after about 25,000 years, half of it should still be there. Okay. A shameless advertising marketing for a movie I just watched last night. It caught me off guard, but I really enjoyed it because like it was impromptu. I never heard anything about it until we decided to go to the movies. We watched this movie called Moonfall with Halle Berry. I really enjoyed it. I felt like they were speaking a lot of truth. Um, they do that a lot in movies. People don't think it's real until they actually experience it. But that's the thing called predictive programming, where they like put things that are like controversial in movies and people just take it as entertainment. Next thing they know, they actually experience it. Another thing is like science fiction oftentimes is a precursor to science fact, right? So like when they introduce these revolutionary ideas in movies, and at that time it's science fiction, people don't think it's real, but then either somebody's already working on it or it inspires somebody to work on it, and then we actually create it. You know, it's like being a human is very interesting because it's like we just don't know of our ability and capabilities. We still think that like, I don't know, it just things oftentimes are not what they seem, and like our ability and things that we can do is like when you put your mind to something, honestly we can do anything. It's really interesting. Really, really interesting. But yeah, anyway, getting back on task. I really did enjoy that movie. 24,755 is called Moonfall. Yeah. So it was fun. Okay. Let's go. I've been leaving the quick checks as an exercise for you, right? So you can see the information here and try it yourself. So then next, we have this example 2. It says the radioactive element carbon-14 has a half-life of 5730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine their age. Archaeologists found that the linen wrapping from one of the Dead Sea Scrolls has lost 22.3% of its carbon-14. What was the linen wrapping? Okay, so for me to remember, if we're doing the half-life formula, KT equals the natural log of 2, right? It says how old equals 22.3% T. Let me think about this. Half-life, right? Wait, let me back up. I'm moving a little bit too fast. I was on autopilot. Right now. We're going to come back to that. It says the radioactive element carbon-14 has a half-life of this, right? So they gave us the half-life. And then the percentage of carbon-14 present, blah, 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 blah. Let me see. Archaeologists found that the linen wrapping from one of the scroll had lost 22.3%. Half-life to find the decay rate. Let me think. If it lost 22.3 T, so this T tells us the half-life. Let me just kind of start crunching. Okay, so like the thing that I'm thinking is like, okay, use this half-life to find the decay rate, and then if it's lost, we want to solve for T, right? Here, let me go ahead and let me do the first part. So 5730, right? So then that means our decay rate is going to be equal to the natural log of 2 over 5730. I might need some more space. natural log of 2 divided by 5730.
Approximately 0.0001200968.
We're just going to use that. Okay, so now if we have our decay rate, now if we're using the exponential decay model, so let me see. Future amount is going to be equal to, is basically per p naught e to the negative kt, right? So we're trying to solve for t. We have our k, we just solve for it. Now, if it says, so you had an initial amount and then the amount now, let me think. The only thing I think that might be a little off, I think this is fine. Let's keep going. 2.3%, right? So it started with P naught. And then now the present amount or the future amount is 22.3% less, right? 100 minus 22, that would put us where? At 78, so 77.7. Hey Siri, what's 100 minus 22.3?
100 minus 22.3 is 77.7.
All right, so then that means the future amount is going to be here. 0.777 of P naught remaining, right? So we start with some amount P naught, and then the rate, I'm just going to use the exact amount, this negative natural log of 2 over 5730. That's our K. Okay. The only thing we don't know is T. Let me give myself some space. That's part of the trouble here. Just rewrite the main part. So again, I'm just using this exponential decay model. I'm going to start with the equal sum, right? Again, we started with P naught. That's how much we started with. If it's lost 22.3%, that means we have 77.7% expressed as a decimal of P naught remaining. Then we can say e to the, we're using the exponential decay model. And then we said negative k, so we got this negative under natural log of 2, like this. I both sides by p naught, so these guys are essentially going to cancel each other out. And then to get that out of the exponent, we take the natural log on both sides. Take the natural log on both sides, right? Okay. So let's account for these changes. So what's going to happen here, this natural log is going to cancel this e, okay? On the left, we're going to have the natural log of 0.777. On the right, that brings it out of the exponent. We get negative natural log of 2 over 5730 times t, okay? Now we just have some number equals some number times t, right? So again, this is just some number equals some number times t. So then if we want to solve for t, divide both sides by that number, right? So then ultimately we'll get t equals, we're going to have the natural log of 0.777 over 2 over 5730. That, right? So this is the exact result, and then we just use a calculator to crunch that number. So let me like having to reload my calculator. I was like, how come? But I'm just so grateful for this. I guess I need to take some time to figure out how to do it myself. I don't know. Anyway, and then let's do it like this. So then here, let's see. So this is going to be equal to, or approximately, natural log of 0.777 divided by negative 25730. Here, let's just do 2085 1086. Okay. It says, how old was the wrapping? About 2086, right? Let's see. So I think we got that same thing. I just kept mine exact until the end. So again, you can see here they're using the Halflife formula, right? I think we got this exact same thing. And then they use exponential decay formula, right? Our labels might be different, but the concepts are the same. 2086. These, you want to do the best you can to not round it to the end. See, notice they wrote out the long decimal, right? Even so, I kept mine exact by just leaving it, I left it in exact form. But as you work these, you want to do if you do write out the decimal, you want to write out the long decimal and keep doing that until you get to the very end. You don't round it to the end. If you truncate and try to round early, it's going to throw this number off, right? So you want to do the best you can to not round it to the very end. The way I do it, I just leave the original formulas whenever possible. Sorry. Let's see what else we got. So quick checks I leave as an exercise for you. So following the birth of their granddaughter, two grandparents want to make an initial investment of P0 that will grow to $10,000 by the child's 20th birthday. Interest is compounded continuously at 4%. What should the initial investment be? Let me give myself some space on this one. That we're dealing with continuous compound interest, right? So I like to write that one as per the future amount. Let me see, A equals is per PE to the RT, right? Which is the future amount. Let's do this. So normally, like, so A equals PE to the RT, right? That this tells us the future amount, but it says we're kind of working backwards, right? We can still plug it in and we could use this form. They give it to us here, right? But this is fine. I'll just use their notation. The future amount equals this. Let me see. To their granddaughter, children want to make an initial investment of P0, that's fine. That will grow to 10,000. So they want P to be $10,000. The biggest thing is having access to the account and just having a little bit of foresight, like, and then you can make life easier for somebody else. And it takes minimal effort on our part. that will grow to $10,000 by the child's 20th birthday. So that means the time is 20 years. Continuously, that's why we're using PERT, and the rate of growth are R. For P naught, okay, this is fine. All right, so let's plug in what we got. So we want the future amount to be 10,000. Let's find out how much we need to start with. Is continuous compound interest, so we're using PERT. The rate, 4% as a decimal, 0.04, and the time is 20 years, right? Right. We're solving for P naught. This guy right here is just a number. So we have our unknown times a number. If we want to solve for our unknown, we use the inverse operation of division to isolate our unknown, right? So long story short, be equal to, you get this e to the 0.04 times 20 is 10,000. We basically divided both sides by that number, right? So then we can just say 10,000, 1, 2, 3, divided by 0.04 times 20. Almost $4,500, right? So we get and $493.29. To start with this way, by the time that the child hits 20, they'll have $10,000. That's fine. I mean, I wish all I need is an account that has that amount. Like 5% was the number that I did a lot of my calculations on, but you know, it's almost like you got to have money to gain access to those accounts. But there are ways to get it done. And I'm telling you, I came this close. Like if you could see me, you know, I'm holding my index finger and thumb finger like really close. I came really close to doing it. I'm actually close again now. Honestly, I'm doing like stocks and trading. And like I was watching it today, like right before I started the stream, like stuff is climbing. I'm no financial guru or anything. So, but yeah, so I'm excited. We'll see what happens. Anyway, all right. Okay, so we got about $4,500 is what needs to go into the account. You see it there, 4493.29. Okay. I want you to notice something about what they did, right? They still started with the continuous compound interest formula. They did the same things we did. They went on to crunch this number. Now notice they divided both sides by the e to the 0.08, right? You have divided by e to this power is the same as e to the negative of that power, right? So then PERT tells us the future is based on the future value. Here, this is a precursor for given some future value if we wanted to find the present value. This into this theorem, right? Present value, P naught, of an amount P due T years later at an interest rate K come out continuously is given by this. So this is what I thought we were about to use in the previous example. I was gonna try to make my way here, but it was fine the way they did it, right? So we saw this come about in that last example we just did. So then the initial deposit, again, the present value P naught of an amount P, so due T years later, at an interest rate K come out continuously is given by this. So this tells us an initial deposit for some future amount, right? it's the same as PERT, just kind of working backwards. So then we have this Newton's law of cooling. The temperature T of a cooling object drops at a rate that is proportional to the difference T minus C, where C is the constant temperature of the surrounding medium. So then we have this dT by, I want to see, T is the temperature of a cooling object. Right? So dt by dt equals negative K times T minus C. So the function that satisfies the above equation is this guy, okay? Based on time. Lumped over a desk. Let's finish this first. Lumped over a desk in a study, the coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. She waits 1 hour, takes the temperature again, and finds it to be 93.4 degrees. Okay. She also notes that the temperature of the room is 70 degrees. When was the murder committed? Right. So let's see if we can do a direct application of Newton's law of cooling. Points. Let's actually do this color. Newton's law, temperature based on time, is this AE to the negative KT plus some constant, right? If we plug in. So some other information that we got, right? She arrives at noon and immediately takes the temperature of the body. So if we let noon, well, here, let's write it like this. At noon, 4.6 degrees. Okay, that's fine. She waits 1 hour, so that means at 1 p.m. 3.4 degrees, right? So we got these 2 times the temperatures. The medium, let me see. So let's put these 2 pieces of information together. Case, I'm going to charge this case. All right. I'm gonna put these. Okay. Like I said, is okay. Let noon be like when the time is 0, right? We're gonna let that be time 0. We got 94.6 degrees. After 1 hour, got 93.4 degrees. Okay. And the room of the room temperature was 70 degrees. Okay. Look at this first point and see what do we have. The temperature based on time. 4.6 degrees equals, we don't know A yet. E, let's see. If 0 times K, right? Because the time was 0. Okay, that's the initial. And then the C is 70. So here, we can solve for A, right? So if we keep going, this is going to collapse because you're going to have basically e to the 0. So this term collapses to 1. Okay. Or we get the 8 equals 94.6 minus 70. So that's what, 24.6. Just to go back and solve for cooling rate. Let me see the other part. Give you some information to what? Solve for K. So then we'll have everything. So then finally we want to solve for T. Okay. All right, let's see. So we got this 93.4 equals this 24.6 e to the negative K plus 7. Right. Only thing we don't know is K. Is this going to help us? Let's keep. If we subtract 70 from both sides, something recursive. 4. 70, we get what? 23.4 equals, there it is, okay, 24.6 e to the negative K. So then e to the negative K equals 23.4 over 24.6 on both sides. K equals the natural log of 23.4 over 24.6. I kind of paused because I was thinking that these two numbers were about to be the same and they're going to cancel each other out and we're going to get a recursive piece of information. I was like, no, we're using different stuff. I just needed to keep going and just see what happened, right? But anyway, so then ultimately the cooling rate the natural log of this 23.4 over 24.6, right? And we just crunch that number to find that. So then if we want to solve for T, let me see. So we have K, we have the temperature based on time. So I think the other piece of information you have to use is, this is where I was pausing. Here, we get a number there, right? But we have all the components. So the only thing I was pausing, I was like, okay, I think you have to use a piece of information that the general temperature of the human body, I think is what, 96.4. I think that was the part that we needed, that I was like, what am I missing? You had like the human body generally is at 96.4. So then be like we just solve for A, but you would have to let T of T, the temperature. So like say before, when the murder happened, that temperature should be 96.4. Let me make sure that number is correct. Blah, blah, blah. If I keep going, I think we got up to here. We just got that, okay. We are. So then it should be something 98.6, right? I knew I didn't know that number. I'm a mathematician, right? So 98.6. I knew it was off. I was like, what is that number? So yeah, we're gonna use that. Okay. So let's put all this together. Let's start there. Let me get it. Can I just paste it? I think I can just paste. Sorry for all the scrolling. Let's together. And I'm gonna leave mine exact. The temperature based on time, we just solved for A. Come on. So then A, right here, you can highlight it. 0.6. 6 e to the, now K, we can go ahead and, that's gonna be a double negative. So I'm gonna go ahead and cancel those out. Natural log 23.4 over 24.6. T, right? So there's no leave the T. And then C we got was 70. Right? The piece of information that we need to use is that, you know, the whole thing about the human body generally is at a temperature of 98.6 degrees. What is that, Fahrenheit? Okay. Murder committed. So then what we're going to do is say 98.6 temperature when the murder was committed, and then basically work backwards. Solve for T. 24.6 e to the natural log of 23.4 over 24.6. Okay. Backwards, subtract 70 on both sides, you get 28, 28.6. I'm going to go ahead and divide by that 24. Yeah, at this point we have e natural log of 23.4 over 24.6 times T. If we take the natural log on both sides to get that out of the exponent, if we take the natural log on both sides, like basically we're doing like natural log of this and natural log of all of this, right? These cancel. Okay. The natural log of 28.6 over 24.6 equals the natural log of 23.4 over 24.6 times T. So that T is going to be the left divided by the right. For 24.6 divided by 23.4 over 24.6. What's this number? Venture. This is approximately log 28.6 divided by 24.6 log of 23.4 divided by 24.6. Um, 1.3. Earlier, so what is that? 9 a.m. Bum bum bum. Huh, this is funny. Okay. So this is a random tangent. This example was about when was the murder committed. In the previews for the movie I saw, they're coming out with another Hercule Poirot movie. I don't know if you know Hercule Poirot. I want to say it's like this series of novels where this is Belgium detective, and he's supposed to be like the world's greatest detective. And so they did, the first movie they did was Murder on the Orient Express with Johnny Depp. You know, Johnny Depp and others, but so they're coming out with another Hercule movie. So I was like, okay, you know, it's kind of fun. Okay, so 3 hours earlier, so then we would say it happened around 9 a.m. That was interesting. I like this kind of stuff. Undo. Yeah. Let's see, how do we do? Yeah. So when time was 0, they got 94.6. So then they got the A was 24.6. I think we got the same thing there. And then after 1 hour, they got 93.4. So then that you can use that to solve for K, right? And so I think we got that same thing, that negative log of all of that. I just left mine in that form instead of rounding. So then they plug those into the Newton's law of cooling formula, all right? So 3.01. The time of death was about 3 hours earlier, or at about 9 a.m. Bum, bum, bum. I need that sound effect. Bum, bum, bum. That sound like anyway, that was fun, right? So then as a summary, as a brief summary for exponential K, let's see. So the decay rate K and the half-life T are related by KT equals natural log of 2. And then again, from here, you can just use division to flow to these other forms. The present value of an amount P, the present value P naught of an amount P due to T is later, and the interest rate K compounded continues is given by this. So this was the conclusion that we came to for a present amount for based on a future amount. And then Newton's law of cooling, the temperature of a cooling object drops at a rate proportional to the difference T minus C, where C is the constant temperature of the surrounding medium. So then dt by dt is this, right? So for some positive K, and we have this guy. And so this one is a solution to this scenario. So those are just some applications of exponential decay. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. All right, guys. So let me do this as well. Well, here, I'll just go ahead and save that for the next one. All right, guys. Take care. Peace.